In today's connected world, data flows between millions of devices across the internet. When you download an image from the internet, how does it travel from a server to your computer? It's thanks to the TCP IP model and its 4 layers: application, transport, network, and link. In this video, we'll show how data flows through these layers. For example, let's use the Mona Lisa image, sent from a server to a client, passing through 8 routers along the way. Each router plays a vital role in directing the data packets through the network, while each layer of the TCP IP model adds specific headers and controls to ensure the data reaches the right place, intact and reliable. Together, these layers and routers work seamlessly to deliver the image across complex networks, highlighting the incredible coordination that happens every time you view a simple image online.
The journey of data begins at the application layer. This layer is where humans directly interact with the network through applications like web browsers, email clients, or streaming services. For our scenario, the client is using a web browser to request an image of the famous Mona Lisa from a server. When the client clicks on the image, the application layer uses the HTTP, Hypertext Transfer Protocol, to send a request to the server. This HTTP request includes several key elements: the URL of the resource being requested, the HTTP method, in this case, a GET request, and headers containing information like the user's browser type, language preferences, and more. Let's break down the HTTP request. The request line specifies the HTTP method and the path to the requested image, /monalisa.jpg. The host field indicates the server to which the request is being sent. The user agent header provides details about the client's browser, and the connection header is used to maintain the connection for future requests, optimizing the communication process. Once the request is structured, it's sent across the network to the server that hosts the Mona Lisa image. The request will pass down through each layer of the TCP IP stack on the client side, get transmitted over the internet, and arrive at the server. On the server side, the application layer receives the HTTP request and processes it. If everything is in order, the server responds with an HTTP response that contains the requested image data. This response includes headers that describe the content type, the size of the image, and other metadata. The HTTP response starts with a status line that indicates whether the request was successful. In this case, we receive a 200 OK status, meaning the server is delivering the image as requested. The content type tells the client that the data being sent is a JPEG image, while the content length specifies the size of the file. With the HTTP response created, including the image data and necessary headers, the server passes this information down to the transport layer, where it will be segmented, encapsulated, and sent over the network to the client.
Before the server can send the Mona Lisa image, the TCP protocol establishes a reliable connection between the server and the client. This process is known as the three-way handshake. First, the client sends a synchronization (SYN) packet to the server, initiating the connection. This packet contains a sequence number to keep track of the data. In response, the server replies with a SYN-ACK packet, acknowledging the client's request and establishing its own sequence number. This packet tells the client, "I received your request, and I'm ready to communicate." Finally, the client sends an acknowledgement (ACK) packet back to the server, confirming that the connection is established. Now, the server can start sending the data, the Mona Lisa image. With the connection established, the server starts transmitting the Mona Lisa image. However, this data can't be sent all at once. It's split into smaller pieces, called TCP segments. The TCP header includes several important fields that facilitate reliable data transmission. Source port indicates the port number on the server that is sending the data, in this case, port 80, which is commonly used for HTTP traffic. Destination port is the port on the client side that receives the data. It's dynamically assigned to match the application requesting the connection. Sequence number field keeps track of the order of bytes being sent, ensuring that each segment of data is reassembled correctly on the client side. Acknowledgement number confirms the receipt of data. It tells the server which byte the client expects next, ensuring that any lost data is retransmitted. Flags are control bits, like ACK, SYN, FIN, manage the connection state. For example, the ACK flag acknowledges received data, while FIN is used to close the connection. Checksum field verifies that the segment's data hasn't been corrupted during transmission. If the checksum doesn't match upon arrival, the segment is discarded, and the server will retransmit it. As the server sends each segment, the client responds with ACK packets, acknowledging the data it has received. This ensures that any lost segments can be retransmitted. If a segment is lost or damaged, TCP automatically resends it, guaranteeing reliable delivery. If a segment is lost, the server will detect the missing acknowledgement and resend the segment. This built-in reliability is what makes TCP so effective for transferring important data, like the Mona Lisa image.
At the network layer, the TCP segments created in the transport layer are encapsulated inside an IP packet. This packet is responsible for ensuring the data reaches the correct destination by assigning IP addresses to both the source, server, and the destination, client. The IP header contains several important fields that help route the data. The source IP address identifies the server sending the data, while the destination IP address ensures it arrives at the client. The TTL, time to live field, limits how many routers the packet can pass through before being discarded, preventing it from endlessly circulating in case of a routing loop. The protocol field tells the network layer that this packet contains a TCP segment, while the checksum ensures the integrity of the header, and identification used to identify fragments of the same packet if fragmentation occurs. As the IP packet moves through the network, it is forwarded by multiple routers. In our case, it passes through 8 routers, R1, 2, or 8, each of which examines the destination IP address to decide the next hop. With every hop, the TTL value is decreased by 1. If the TTL reaches 0 before the packet reaches its destination, the packet is discarded, and an error message is generated. Sometimes, the packet may be too large to be transmitted across a particular network due to differences in the maximum transmission unit, MTU. In this case, the packet is fragmented into smaller pieces to fit within the allowed size. For example, the MTU at R4 is only 620 bytes, while the server is sending a payload of 1400 bytes. Therefore, the packet must be fragmented. Let's break down the fragmentation process in detail. The total packet size is 1420 bytes, where 1400 bytes of data plus a 20-byte IP header. The MTU at router R4 allows only 620 bytes per fragment. However, 20 bytes are reserved for the IP header, meaning that only 600 bytes are available for the payload in each fragment. The first two fragments each carry 600 bytes of payload and 20 bytes of IP header. The final fragment carries the remaining 200 bytes of payload with its own 20-byte IP header, making it 220 bytes. Each fragment is assigned a unique IP header, but they all share the same identification field, so they can be reassembled at the destination. Each fragment is assigned a fragment offset, which is multiple of 8, to ensure that the client can reassemble them correctly. Once all fragments reach the destination, they are pieced back together to recreate the original IP packet. Sometimes, issues occur during packet transmission, such as a TTL expiration or network unreachable errors. In such cases, the ICMP protocol is used to send error messages and diagnostics. For example, if the TTL reaches 0 before the packet arrives at the client, the router discards the packet and sends back an ICMP time exceeded message to the server, letting it know there's an issue. ICMP is crucial for network troubleshooting and diagnostics. It is used by tools like ping and traceroute to help identify where in the network the problem is occurring. It allows network devices to communicate about errors and failures so that issues can be resolved. Once the IP packet has successfully navigated through the routers and avoided fragmentation or TTL expiration, it arrives at its final destination, the client. The next layer, the link layer, takes over from here to deliver the packet to the client's network interface.
In this section, we'll explore the process of creating the Ethernet header and break down its various subparts. Here, we have the network layer, responsible for packaging data into IP packets. Now, as the IP packet moves from the network layer to the data link layer, it's prepared for transmission over the physical network. The data link layer encapsulates the IP packet into an Ethernet frame. This process involves adding an Ethernet header, which includes essential details such as the source and destination MAC addresses and the ether type. These components ensure that the data is properly addressed and can be transmitted across the local network. Finally, the frame includes a frame check sequence. Now that we've covered the full Ethernet header structure, let's dive into each part one by one to understand their functions. The source MAC address shows where the data is coming from. It's important because the receiving device needs to know who sent the data so it can send a reply back to the right place. The destination MAC address tells the network where the data is going. It's essential because it ensures that the data reaches the correct device on the network. The ether type field indicates what kind of data is inside the Ethernet frame. It tells the receiving device how to process the payload, like whether it's an IPv4 packet or another type of data. The payload is the actual data being transmitted inside the Ethernet frame. It can include anything from an IP packet to other types of data. This is the main content that needs to reach the destination. The frame check sequence, or FCS, is used to detect errors in the Ethernet frame. It helps ensure that the data wasn't corrupted during transmission. After the Ethernet frame is fully constructed with the header and payload, it's sent to the physical layer. With that, we wrap up our discussion on the Ethernet header and see you again. But before sending the frame, the server must know the MAC address of the next top device. Since the server only knows the client's IP address, it uses the Address Resolution Protocol, ARP, to find out the corresponding MAC address. The server sends an ARP request as a broadcast message to the network, asking who has IP address 192.168.1.10. This request includes the server's own IP and MAC addresses. The client recognizes its IP address in the ARP request and responds with an ARP reply, providing its MAC address to the server. Now that the server has both the IP and MAC address of the client, it can create the frame and begin transmission.
From the server to the client, each layer of the TCP IP model played a critical role in the journey of our Mona Lisa image. The application layer prepared the data, the transport layer ensured it was reliable, the network layer guided it across complex paths, and the link layer delivered it to its final destination. This intricate dance of headers, handshakes, packets, and protocols happens in milliseconds, hidden behind every click, every request, and every image you see online. In the world of digital communication, every image, message, and video is the result of countless technologies working seamlessly together. The next time you download a picture or send a file, remember the incredible voyage your data takes crossing boundaries, overcoming obstacles, and arriving precisely where it needs to be. The TCP IP model is not just a technical standard. It's the silent engine driving our connected world. Thank you for joining us on this journey through the TCP IP model where every bit counts.